Speaker.
Welcome to Monday's program. So today it's my honor to introduce the speaker, Professor Takahiro Hasebe from Hokkaido University. And his research field is free probability, mathematics, quantum information. So the title of his talk is cyclic-Independence, Boolean and monotone. So let's welcome him.
I'm glad to visit Taiwan. So this is my second time to visit Taiwan. The first time was Kaohsiung. In both times, Professor Hokkaido invited me. And yesterday, Howie Huang took me to Beirut, and we had a lot of tea there. And I feel I became healthy after a lot of teas. And ready to give a talk. So this talk is about some free probability, or more general non-commutative probability, what people say. And this is kind of a extension of probability theory to non-commutative setting that comes from quantum physics. But this talk is not so related to quantum physics, at least directly. Maybe there are some applications. And today I'd like to start from a certain graph theory, because non-commutative probability found some relations to graph theory so far. Okay, so let's consider. So in graph theory, there are several operations, binary operations. I will tell you certain examples, some examples. So firstly, I will think of two graphs. So for now, let me assume they are finite and simple. Simple means no loops, no multiple edges. And there is a certain binary operation called the Cartesian product that is usually denoted by cross. What is this? It's much easier to understand by examples. So let me some colors. Let me take triangle and then take the Cartesian product with say some line with 3 vertices. So the product of those two guys is first. So this is supposed to be G1, and the blue line is supposed to be G2, and the Cartesian product of the 3, this is first I write copies of G1, 3 copies, like this. And connect them in a vertical direction by G2. So that means G2 here, and here, here. This is called the Cartesian product. I will give you another example. How about triangle and also triangle? So how does the product look like? Again, so this is equal to, this is a definition. This is a definition. So first, again, take 3 copies, like this, and then to the vertical direction, we connect these 3 points by G2. So that means maybe it's, I think it's better to move the second one a little bit to the right, like this. Then connect those 3 points by G2. And here also, this and this, and finally, like this. Of course, there is general definition, but I will not give detailed definition. Okay, so actually there are more operations. So this Cartesian product is associative and also commutative. So commutative means there is some natural identification of G1 times G2 and G2 times G1. And there are more examples of such operations. And another example is what I call star product, G1 star G2. But I think this name may be different in other fields. More precisely, to define star product, G1 and G2 assumed to be rooted graph. For example, so this is G1, and let me specify a root by another circle here. So this is called the root. The star product is actually very simple. So we just take another graph here with root and connect them by the root. So the definition is just this, and this. Maybe it's 1, 2. It's also easy to check that this is associative operation and also commutative in the, say, category of rooted graphs. This is perhaps the simplest graph product. A bit more complicated one I want to introduce. G1 and I think this notation. Okay. So we take the same two graphs and take the so-called home product. This is you just put the second graph to each vertex of the first graph. So what you get is this, and maybe better to write the root at the bottom. And what I want to tell you today is to study the eigenvalues of the so-called adjacency matrices of those graphs. So each have adjacency matrix and the certain eigenvalues of the matrices. Then what happens for the eigenvalues for the product of the graph? And in order to compute the eigenvalues of the adjacency matrix, some non-commutative probability techniques are useful. Okay, so nextly, adjacency matrix. So this is just a matrix whose entries are 0 or 1, and 0 if two vertices are disconnected, and 1 if two vertices are connected. And also easy to understand by example. If G is such a line, the adjacency matrix AG, okay, so in this case, it's better to label the vertices, say 1 to 3. Then this, it's adjacency matrix. This is first the diagonal entries are all 0, and between 1 and 2 there is an edge, so that means 1 and 1 here. And 2 and 3, there is an edge, so that means 1 and 1 here. Between 1 and 3, there is no edge, that means zeros for 1, 3 and 3, 1 entries. So what happens for the adjacency matrix of the product of graphs? For the Cartesian product, adjacency matrix of the Cartesian product of two graphs, this can be written in the following way: A G1 tensor identity matrix plus identity matrix tensor A G2. And I think I should explain the meaning of this tensor notation. So here I'm using the following identification. So adjacency matrix AG can be regarded as a linear operator maybe let me say L of L2B. So B is a set of vertices. BG is a set of vertices. Then adjacency matrix can be regarded as a linear operator on L2BG. But of course, when G is a finite set, this is a, I write L2, but this is just a function space over finite set. So this L2BG, this is just C2BG. And then the vertex set of Cartesian product, this is just the vertex set of Cartesian product is just VG1 times VG2. That's a direct product of two sets. Then the function space L2VG has a canonical isomorphism to the function space of VG1 tensor product VG2. Maybe I should write this. So this is a function space. Okay, so under this identification, we have this decomposition formula for the adjacency matrix of Cartesian product. Maybe later I will explain more about some more intuitive interpretation of this formula. For now, I'd like to go to the second example of star product. So to describe the adjacency matrix of the star product, this itself is not so complicated. So, but for later use, I'd like to embed the star product into the Cartesian product. This is there's some simple embedding. So we can regard the star product G1 and G2 as a kind of subgraph of G1 times G2. So how to do this? So one way is as follows. There are several ways. So in this example, G1 is triangle and G2 is this 3-point line. Let's take this part. The bottom graph, bottom copy of G1, and here is G2. This is just a star product of G1, G2. So if we regard a star product in this way as a subgraph, then correspondingly we can write the adjacency matrix G1 star G2. This is AG1 tensor. Here comes not identity, but let me write some projection. And similarly, P1 some projection and AG2. So such a decomposition. And here P1 and P2, this is orthogonal projection. Maybe PI. Okay. Orthogonal projection onto the one-dimensional subspace spanned by the root. Spanned by the root. So what I mean is Pi is a linear operator from so Pi is a linear operator on L2 V G I, and the delta root is a unit vector in L2V G1 GI. And this delta root, this is a function on the VGI defined by 0 or 1. And 1 if V is the root. 0 otherwise. By the way, if you have a question during my talk, feel free to ask me. So far, any questions? All right. Okay, let me briefly explain this intuitive interpretation of decomposition formula. In the star product case, how to interpret this? So, in the Cartesian product, we have 3 copies of G1. G1 here, here, here. And also 3 copies of G2. This line, and this line, and this line. And the meaning of this formula is, so this is a projection onto the root. So this means among these 3 G1s, only this guy vertices are connected. So remember that the star product is also this and this, those 2 parts. This is a star product. And those 3 points are disconnected. Those 3 points are also disconnected. And only those 3 points are connected. So basically that's expressed by this P2. P2 is also a projection, and kind of a root is here. So maybe I should have write down here. So this is a root. And among those 3 components, so kind of so this is this direction. So this is like first floor, second floor, third floor. And the projection means neglect second and second and third floor. Only look at the first floor. This is the meaning of tensor projection. Similarly, for the second part, we have orthogonal projection on the first component. This is similar. So in the Cartesian product, we have 3 G2s, vertical lines. Among those 3, so maybe this direction. Just neglect the second line and the third line. Only the first line, the vertices are connected by edges. So this is basically the meaning of this P1. Neglect the second and the third lines. On the other hand, for the Cartesian product, you have this identity. So identity means don't neglect any lines, any graphs. So the Cartesian product, so all the copies G1 are connected. So here is connected, here is also connected, no deletion. So that's the meaning of identity matrix here. Okay, so for the third product, home product, so maybe this is 2, and now put 3. again, we can regard the cone product G1, G2 as a subgraph of the Cartesian product G1, G2. One natural embedding is as follows. So I again use the same example. So triangle, triangle, 3 triangles and 3 vertical lines. Like this. Or maybe dots looks better. For the cone product, we take the bottom G1 and these 3 lines. And here is a root. And neglect the second floor and the third floor. This is a cone product. Realized as a subgraph of a Cartesian product. So the vertex set actually is the same as the Cartesian product. But there are less edges. Namely, on the second floor and the third floor, edges are deleted. That's the cone product. What happens for the adjacency matrix of this graph? So this is A, G1, G2 is in the same vein as before, in the same idea. So this is A1, AG1, tensor product P2 plus here is identity matrix tensor product AG2. So this is quite similar to the previous case. So we have 2 directions. For the vertical direction, we delete the third floor and the second floor. So this is G1 and the blue is G2. But for the vertical direction, so there are 3 G2 and the edges of G2 are not deleted. So that's why here is identity. Okay, then now I will go to computing the eigenvalues of such a adjacency matrix of a product of graphs. So in order to compute eigenvalues, one useful method is to compute the traces of those matrices, powers of matrices actually. To compute the trace of AG to the K, for any K. There are several ways to recover eigenvalues from these informations. For example, so suppose we are somehow we are able to compute these values, then we can introduce such a generating function. Let me write a small g, maybe AG. So this is defined by trace, and we take the resolvent z h. So let's consider such a function. In our joint work, we call this function the Cauchy transform. I'm not quite sure if this terminology is the best one. So if you have some suggestion for the terminologies, please tell me during the talk or later. So for now, so if there is no obligation, let me call this Cauchy transform of G or AG. So if we use this, we can recover the eigenvalues of AG, because with G we can recover the eigenvalues of AG from traces. This is because, so on one hand, this Cauchy transform GAG of Z, this has the expression 1 over Z minus lambda I. I is 1 to some number by functional calculus. On the other hand, if we expand this resolvent into series, Laurent series, we can get this is on the other hand trace of infinite sum of z to n plus 1. Maybe n is already used, so z to k plus 1 and a g to the k, and k is from 0 to infinity. Just expand this resolvent into series. We get this. Then this can be written as if okay, we are allowed to exchange trace and sum in a suitable region. So we get trace HE to the k over z is k plus 1. So from this formula, if we can somehow compute this trace, then we can detect the eigenvalues as poles of this function. Okay, so let's try to compute such a traces for these adjacency matrices. Well, okay, let me first try this cone product case. So of course, first we have to compute the power. So H1, G2 to the K. What is this? So because of this decomposition, this can be written as a sum of a lot of terms. For example, we will see such a term, A G1. Okay, let me use some shorter notation, just A1 instead of AG1. So, for example, we have such a term, A1 tensor P2 and I tensor P2 times let's say for K equal to 3. Okay, no, let's say K equal to 4. And in the computation of this power, we see such a term. And this can be computed like this. So this is just A1 square tensor P2, A2, P2, A2. Then take the trace of this guy. What happens? So for simplicity, this is, let me write this as x. Then trace x. What is this? Trace of the tensor product just is trace of each tensor component. So this is just trace A1 square times trace of P2, A2, P2, A2. Okay, so trace of A1 square, this is more or less known. So suppose this is known. A1 and A2 are well known. Let's suppose so. But how about the second term? Trace of P2A2, P2A2. There are two P2s in between. Actually, this can be simplified more because we have such an identity. P2, A2, P2. So this is actually equal to so this is delta root. Maybe I will write it like this. And A2 delta root times B. So remember that P2 is an orthogonal projection from L2BG2 to the one-dimensional subspace spanned by the root. this is very easy formula. So let me use this. Okay, so if we use this, then trace x is just trace a1 square times trace of inner product and this is a scalar, so let's take it out from the trace. So this times trace of a2. No. Iterated. Well, this is a trace iterated, so we can use some certain trick for the last part, because P2 is projection, right? So we can also write P2 square. And because this is a trace, we can take one P2 to the right. So just write in this way. This is allowed. Then we can again use that formula. So this is just a trace of A2 and again the inner product.
Repeat. Trace of P2.
Trace of yes. Yes. Trace of P2, yes. And this is 1. This is just 1. Alright, so we arrive at trace A1 square times the inner product. Delta R A2 delta R square. Such a formula appears. So you can see that in order to compute traces of the adjacency matrix, we need trace of the first graph and the certain inner product for the second graph. Then we can compute. And for there are other terms, but they are all similar. You can compute similarly. So eventually, you will see that what we need is we can compute trace of AG1, G2 the home product to any k in terms of trace of E1 L, so L is natural number, and inner product. But here, in general, A2 power appears. Because sometimes we have to take identity tensor A2 and the next can be also identity tensor A2. So if this identity tensor A2 appears continuously several times, then you will get the A2 to power something. So for this we need such powers.
So what kind of dependency is that?
So this is actually some formula appearing in random matrices.
So what kind of dependency? Do you have a name?
Yeah, actually it was named in my paper with Benoit Colling and Noriyoshi Sakuma, and we call it cyclic-monotone independence.
And suppose k is fixed, so one number for L, we need to compute the trace of k.
One number.
Because when k is 4, we just need to know the second moment
Yes.
and A2 to the second. So L has to be less than equal to k or
Yes.
less than k?
Yes, less than or equal to k in general. All right, so so far any questions? Okay. So let me, how to say, summarize or state the results in an abstract setting. So in a way, what we call independence. So what I have shown you is a certain example of independence in non-commutative probability. But this is some new example. Maybe not new. So something appeared in random matrices. So a bit in a general setting, I will formulate. So the definition. So let's take some A, which is algebra over the complex field. This is supposed to be just linear operators on the vertices. So this is supposed to be e.g. A's L of V G1 times G2. No, function space. So this is an example. And let's take two linear functionals, phi and omega. So they are linear functions from A to C. And for phi, I will assume that the unit element is sent to the unit. So phi 1 is 1. So they are abstraction of this inner product. So phi x is some root inner product of x delta. And omega is just a trace. These are typical examples. I will take off. Okay. So we take subalgebras A1, A2, A. They are subalgebras. Okay, yes, it's E1, E2. So we call A1 and A2 are cyclic monotone independent, independent. If we have the following calculation formulas, so for any A1, A2, AK from algebra A1 and B1, B2, maybe BK from algebra A2, sorry, B1, BK. We have, so we want to compute such kind of omega A1, B1, A2, B2 up to AK, BK. If this is computed by omega of A1, A2 up to AK times phi B1, phi B2 times up to phi BK. This is abstract version of computations from here. And actually, sometimes we need to compute also for phi. And for phi, I haven't shown you, but we can get something like that: A1, B1, A2, B2, AK, BK, and this is very similar. A1, A2, up to AK, and then phi B1, phi B2, phi BK. And so we want to compute omega. This is a, you can think this is a trace. Omega of say A plus B to the K, where A is from algebra A1 and B is from algebra A2. This is basically what we need to do. And this is much simpler because we don't have this tensor notation. So notation is much simpler for this abstract setting.
Maybe you still have 2 minutes.
Oh, okay. Okay, maybe let me write the formula for this omega, but not exactly for omega, but for the generating functions. So let's define the generating function also in a general setting. So this is the sum from a n to 0 infinity and v to k, k plus 1 and omega v to k. And then GA, capital GA is similar but for phi. Phi equals k. Okay, maybe let me write this as a main theorem. So in the previous setting, after a lot of combinatorial arguments, maybe not so long, but we can compute small g a plus b. This is gbz plus GA, small ga, and 1 over capital G B times 1 over capital Z prime. So this is for two cases. Only the product of two graphs. In a paper with Franz Renner and Octavio Arismendi, we also computed firstly. So this is for home product, but there is also a formula for the star product, which is simpler actually. And we also computed some certain limit theorem. So this is for two graphs, but what happens if we iterate the graph product many times and take the limit? Then we can get certain limit theorem for eigenvalues. But I will skip it, so I will stop here.
Questions for the speaker?
So for this theorem, we need to capital G information.
Yes, so here appears capital G.
Yeah, and for capital G A plus B, we need to calculate this one.
Okay, so you are thinking this one?
Yeah, so we need this one.
For this, no. But if we iterate, for example, if we want to compute something like this, then you can see here appears G, B plus C. So we need to compute this.
So based on this formula, we are able to know any information about A plus B?
Yes.
Only
yes.
little g is enough? Only little g is enough
Yes.
to
Yes.
recover
Yes.
all the information about
Yes,
A plus
yes.
B?
Yes. You can just use this formula and look at the poles of this function. Then you get eigenvalues. Maybe I should say that this formula is a kind of a reformulation of some known formula known in 1970s.
But little g tells you information about omega, and capital G tells you information about phi. But if you are given the little g, how about the information about phi? Do we know about that?
From little g, maybe impossible. We need both.
But you tell me that we just need to know little g of A plus B. We don't need to care about capital G of.
Yes, in order to compute the eigenvalues of this A plus B, then little g is enough.
Oh, eigenvalues. Okay. Okay. So, any questions for the speaker? If not, let's send our speaker again. How about let's take a short break and let's do at 4:30, okay?